All right, if I'm following your schedule correctly, it seems like from what you sent, you're going to start off with a bit of review on U substitution, but that should be review. And then you're going to get into hyperbolic functions. And that seems to correspond to a I think it's chapter 7 in your book, and it's actually chapter 7 in a lot of textbooks. So um, I'm going to go ahead and kick off then with this, which is um, this is the from the textbook that you used, and I don't know if you brought it with you. Hopefully you did. If you didn't, we can send it to you. But this should chapter 7 from the text used for Calc 1 should match that. And so we're going to discuss logarithmic and exponential functions to start, and then hyperbolics immediately afterwards. But let's start here with logarithmic, exponential, hyperbolic functions. We're going to start with revisiting logarithmic and exponential functions. And the reason for that is because, well, we learned a bit about um, logarithmic and exponential functions, but we really didn't. Um, we took a lot of it on faith, and I'll show you what I mean by that. Okay, apparently forgot to hit resume recording, so don't know where I was. So let me go back to where I think I was, which is we're talking about the exponential function. So that's e to the x, and we're talking about its inverse, which is the natural log of x. And so if these are inverses, remember f of f inverse of x equals f inverse of f of x, which gives you x back. And so that means e to the natural log of x is going to be x, and the natural log of e to the x is going to be x also. Okay. So that when we first introduced the exponential and we first introduced the logarithm, we know that's the relationship between two of them. We said a couple of other things. We said that the domain of e to the x is all real numbers, but the range of e to the x is positive only. And so that means that the domain, because the domain of the function is the range of the inverse, so that means the range of the natural log of x is going to be uh, all real numbers, and the domain of the natural log of x would be positives only. Okay. Now we know a couple of other things. We stated them without proof. We just sort of took them on faith. One is the continuity, and that's kind of implied by the domain thing. We also said that they were uh, differentiable and integrable over their domains. Okay, but we didn't really prove that. We just said that that's the case, and we didn't kind of go into it anymore. And so what this chapter will do is this chapter will build that out a little bit more, provide you with a little bit more of a background and understanding on those two functions. Okay, so let's start with the natural logarithm. And we defined it a couple of ways. Mainly, we defined it as the inverse of the exponential function. But another definition of the natural logarithm is to define it as an integral function. That is a function that is defined in terms of a integral. And that would be that the natural log of x is the integral from 1 to x of 1 over t dt. Okay, that's one way to define it. And that would mean then if y equals 1 over t, then if we integrate from 1 to x, that function, the net area, would be the natural log of x. Now, another thing that kind of comes out of that is you'll recall the fundamental theorem of calculus. So if we jump back to the whiteboard here and we look at the natural log of x a little bit more. Okay, so we're saying, hey, we can define the natural log of x as this integral function, the integral from 1 to x of 1 over t dt. Remember, the fundamental theorem says that if I take the derivative with respect to x of the integral from 1 to x of 1 over t dt, that would give me 1 over x. Okay, and so that means that's where we get the idea then that the derivative with respect to x of the natural log is 1 over x. Okay, we just sort of stated that before, but it comes from this definition. All right, so now let's jump back here to this. And so that means, right, that since we're defining the natural log as the integral from 1 to x of 1 over t dt, and that area will always be, sorry, I had a bit of a cat interruption there. Okay, so as we were saying, since we can define the natural log function this way, we note that whenever we're greater than 1, so if we're integrating 1 over t from t equals 1 to t equals something greater than 1, that's always going to be positive, right? That's always going to give you a positive number. So the implication being the natural log of anything greater than 1 is going to give you something greater than 0. But let's note another property here, and we'll jump to the whiteboard again. All right, so if we go back to looking at our function, right, if y equals 1 over t, we note that t cannot equal 0, and so the integral from 1 to x of 1 over t dt only exists on 0 to infinity. All right, can't exist for 0, only exists at 0 to infinity. And so, you know, that makes sense if this is the natural log. We said the domain of the natural log is positive numbers only. The other thing that we note, we already talked about whenever x is greater than 1, that area is going to be positive, and so the natural log function is going to be positive. But whenever x is greater than 0 but less than 1, we have that the integral from 1 to x of 1 over t dt is going to equal the negative integral from x to 1 of 1 over t dt, okay, which implies that the natural log of x is less than 0 if x is between 0 and 1. Okay, so the net area interpretation here implies that that the range of the natural log of x then would be negative infinity to positive infinity, and that makes sense because the domain of its inverse, the exponential function, is all real numbers. Okay, so that makes sense, that we would expect that to be the case. Okay, so this is just stating what we were just talking about. Whenever x is between 0 and 1, the natural log we expect to be negative. Okay, and then we get the following important. We just talked about the fundamental theorem of calculus, right? And how that says that means the derivative of the natural log of x would be 1 over x. And so we can see here that since the derivative of the natural log of x is 1 over x, we know that the derivative is greater than 0 everywhere. Because if we look at the natural log function, it is increasing everywhere. Okay, it's increasing for x greater than 0. And if we go back and look at the function 1 over x for x greater than 0, it's always positive, right? It's always positive. And since 1 over x is the derivative of the log, that makes sense that the log is therefore increasing everywhere. Okay. A couple of things about it we can look at. The derivative we just talked about, the limit as x goes to positive infinity of the natural log is infinity. As we go to 0 from above, okay, from the positive direction, we see that the natural log, the limit as x goes to 0 from above the natural log is negative infinity. Okay, it goes to negative infinity as we get closer to 0. And the second derivative of the log is less than 0, okay, on its domain, because, well, let's go ahead and do that real quick. So the derivative of the logarithm we just said, and let's jump to our whiteboard. We can do a little quick proof of that. Remember, the range here is x 0 to infinity, so we're only worried about x greater than 0. And the derivative of the logarithm is 1 over x, which on 0 to infinity is always greater than 0. Okay, so that means we're increasing on the 0 to infinity. The second derivative of the natural log would be the derivative of 1 over x, which we can write as x to the minus 1. And so that's going to be negative x to the minus 2, which is negative 1 over x squared, which for x greater than 0 is going to be less than 0. And so that implies on its domain that we are concave down. Okay, that's our second derivative test, if you remember from Calc 1. Okay, so concave down everywhere also. And so let's roll all of these up into the properties of the natural log here. We have that the domain and range of the natural log of x are 0 to infinity for the domain, and all real numbers, negative infinity to positive infinity for the range. The natural log of xy equals the, actually, you know what, we should do that as a proof real quick. I think we've kind of taken it for granted, so let's just go ahead and illustrate that as a quick proof. Natural log of xy. All right, so we're just going to illustrate this one property, prove the one property. So here we go. Natural log of xy. We can write that in terms of the integral as the integral from 1 to xy of 1 over t dt. Now we can use the additive property of integrals, then write that as the integral from 1 to x of 1 over t dt plus the integral from x to xy of 1 over t dt. Okay, that's just the additive. We're just breaking that this range of integration into pieces, and then we can do a substitution. We can do the u substitution, u equals t over x. Okay, and if I do the substitution, u equals t over x in the second integral, so we're going to do that here, and that's going to give us the integral from 1 to x of 1 over t dt. And then this becomes, okay, if u is t over x, and then that's going to become the integral from 1 to y of 1 over u du. Okay, so that would mean all right, so then that breaks with that u substitution, the second integral then, right? This we can convert back using the pattern, right? Integral from 1 to x of 1 over t dt. So this is just the log of x. The integral from 1 to y of 1 over u du then just becomes the log of y. So we have the natural log of xy is the natural log of x plus the natural log of y. And that's the well-known property of the logarithm turning products into sums. So going back to our properties there, we can do a similar process to show number 3, that it turns a quotient into a difference, and so on. So these are the properties of the logs that we've seen before. Okay, and number 7 is going to be important for us for what follows, that the integral from of 1 over x dx is the natural log of the absolute value of x plus c. Okay, so we're going to make use of that. 5 and 6, we've just kind of, well, 5 we've proven in several different ways just now, and 6 is just the chain applied to the natural log. So using our symmetry about the line y equals x rule, we can look at the natural log and then see what its inverse function, the exponential, looks like. Okay, so that's the red curve there, y equals e to the x, or the exponential of x. So again, one that we've already seen and kind of played with. And so that brings us to another definition of that special number e. Okay, the number e is that real number that satisfies the natural log of e equals the integral from 1 to e of dt over t equals 1. Okay, so it satisfies the natural log of e equals 1. Okay. Now that definition is simply saying that the area bounded by the curve y equals 1 over t and the t-axis between 1 and this number e equals 1. Okay, and we know that the natural log of 2 is less than 1. We know that the natural log of 3 is going to be greater than 1, right? So if we calculate the area of 1 over t between 1 and 2, we're going to get something less than 1. If we calculate the area of 1 over t under 1 over t between 1 and 3, we're going to get something greater than 1. And since the area under y equals 1 over t between 1 and e has to equal 1, that tells us that that number e is somewhere between 2 and 3. Okay, a little bit closer to 3 than it is to 2, but that tells us that e has to live somewhere between 2 and 3. And so that gives us another definition, another way to define the exponential function, where for any real number x, y equals e to the x, or the exponential function of x, where x is the natural log of y. So properties of e to the x. Okay, the exponential function satisfies the following properties. Again, we've kind of seen these before, although we mainly kind of took them as given, but the again, the exponential turns, whereas you can kind of view it as the logarithm turning products into sums, the exponential kind of does it the other way, right? So e to the x plus y equals e to the x times e to the y. E to the x minus y is e to the x divided by e to the y. E to the x quantity to the p is e to the xp when p is rational. Because the log and the exponential are inverses of each other, the natural log of e to the x is going to be x, and e to the natural log of x is going to be x. Okay, so that leads us to the derivative and the integral of the exponential function. Again, things that we sort of stated before, but really didn't prove, and we'll see them again here, which is the derivative of the exponential function is just the exponential function. And the integral of the exponential function is just the exponential function. Okay, so this theorem here states it in terms of the chain rule, right? The derivative with respect to x of e to the u of x is going to be e to the u of x, u prime of x, just a chain rule there. And integrating the exponential gives you the exponential function again. Okay. All right. Almost done here. Change of base formula is next. The change of base formula just allows you to write any exponential base in terms of that number e. So if b is a positive real number, or b is not equal to 1, then for all real x, b to the x can be written as e to the x natural log of b. Okay, to summarize, then where b is greater than 0 but not equal to 1, the derivative of the log base b of a function u of x will be 1 over log b, u prime of x, u of x. Okay, so we also have, remember, the change of base formula for the log. So let me jump here and just kind of refresh your memory. We stated before log base b of x, we could write that as the natural log of x over the natural log of b. Okay, so if you have the log base b of u of x, then we would just be writing that as the natural log of u of x over the natural log of b. And so we can pull 1 over natural log of b out, just dealing with the natural log of u of x. And so if I take its derivative, 1 over log b, this is just a constant. And so derivative of natural log is 1 over u. So it's 1 over u of x, u prime of x. Okay, so that's where that comes from. Okay, and similar idea with b to the u of x, that same thing, e to the, since b to the x can be written as e to the x natural log of b, just making that substitution to start and then applying the idea that the derivative of e to the x is e to the x. And that's what gives us these formulas there. Okay, so then that can lead to the general power rule for any real number. Prior to that, we had it for rational numbers, but we can define it for any real number p. The general power rule is the same as the old power, right? Derivative d dx of x to the p is p x to the p minus 1 for any real number p. Okay, now since we've defined the exponentials and the logarithms, right? To cover the all real numbers like we needed. There we have it. So, all right, final thing is, how do you compute E? What is that number? We know that it's somewhere between 2 and 3, but what is it exactly? One way that we can do that, so we know that it's the base of the natural log function and the exponential function, but what does that mean? How do we approximate the value? We know that the derivative of the natural log at x equals 1 has to equal 1. By the definition, then, so this is probably a good exercise. So we'll do that real quick here. So by definition, the derivative of the natural log of x at x equals 1 should be 1. So we'll just state that right here. Okay, the derivative of the natural log of x evaluated at x equals 1 should equal 1. Now let's apply the definition of the derivative at x equals 1. That would be the limit as h goes to 0 of the natural log of 1 plus h minus the natural log of 1 over h. The natural log of 1, though, is 0, and so this should reduce to limit as h goes to infinity of the natural log of 1 plus h over h. And using the power rule there, okay, then that can be written as the natural log of 1 plus h to the 1 over h. All right, now, since the logarithm is continuous for x greater than 0, all right, so we're continuous for x greater than 0. And so that means, right, the limit should be able to be carried inside. So the limit as h approaches 0, or sorry, h approaches infinity. No, not h approaches 0. Sorry, this should be 0. My writing's a little sloppy there. 1 plus h to the 1 over h. And that should equal 1. Okay, so that means that the limit, since the natural log of this limit equals 1, and the natural log of e equals 1, this limit right here should equal the number e. And so if we evaluate that limit for increasingly large values, or sorry, increasingly small values of, as h goes to 0, increasingly small values of h, we should get closer and closer to the number e. Okay, and so we can look for 1/10 when h equals 0.1, right? That limit gives you 2.59. When h is 0.01, you get 2.7, and so on. And you can approach this from either side of 0. Okay, so you can get negative 0.1, negative 0.01, negative 0.001, and so on. And you'll notice that you're approaching the closer we get to 0 from either side, we get closer and closer to this number 2.718282, and so on. Okay, so in the limit, we see that we get a value 2.718 something. Okay, that number is in fact a transcendental number similar to pi. Okay, and that means that that is a number, decimal that never ends, never repeats. It's similar to pi. It's been computed to millions of digits, but it's again one of those cool transcendental numbers that we have like pi. Okay, so that's the number E. That is the little bit about the logarithm and the exponential function and some of their properties. And next time, then we'll talk about we'll talk a little bit about hyperbolics.